Thank you very much. Well, I want to thank all the organizers for the invitation for the talk today, and of course, all of you for attending because you read the abstract and you didn't escape. So I thank you your attendance. Today I want to talk about the Daugavet property in spaces of vector-valued Lipschitz functions. I'm very happy to present this talk because this is a problem I have tried for maybe 6 or 7 years. But before entering in details, I want to be serious and present my sponsors in order to avoid legal problems. Okay? And I want to keep being serious, but it is for me now a big pleasure to introduce you my collaborator in this story. He's Rubén Medina. He is currently at Public University of Pamplona, but he was previously a PhD student in Granada. And all this project started when I moved from Murcia to Granada in 2023. We thought that we could take advantage of his very big expertise on Lipschitz function spaces and my modest knowledge on Daugavet property. And all the results I'm presenting here are in collaboration with him. Okay, let's begin introducing necessary definition. We will introduce the Lipschitz free spaces and Lipschitz function spaces. We will consider complete metric spaces M. This is not any loss of generality, and we will consider a distinguished point in our metric, which we call 0 for convenience. And given any Banach space X, we consider Lip0 of Mx the space of all the Lipschitz functions from M to X, which vanish at our distinguished point, which is a Banach space when endowed with the classical Lipschitz seminor given by the best Lipschitz constant. The fact that our Lip0 contains no other constant function but the 0 function makes this seminor into a norm, and it is even complete. We will avoid the reference to the Banach space when it is a scalar field, which will be R, in order to take advantage of Max-N extension theorem. Okay, this space is a Banach space, but even more, the real value Lipschitz function space is even a dual Banach space. And in order to give a description of the pre-dual, we can consider the evaluation mapping delta M in the same way as we do in spaces of continuous functions. It is a functional which acts as Lipschitz function just evaluating at the point. It is linear and continuous, and it turns out that if one defines f of n as the linear expansion of these evaluation mappings, what we get is a Banach space whose topological dual is isometrically isomorphic to Lip0 of M. This f of M is what is known in the literature as the Lipschitz free space over M. Well, this space is also very well known because people say, or it is roughly said, that Lipschitz free space spaces linearize Lipschitz functions. And in the formal way in which we can say that is that whenever we have a Lipschitz mapping from M to X, which vanishes at our distinguished point, then we can define a bounded operator hat F from f of M into X, defined simply acting on evaluation mapping, just evaluating, and extending by linearity and continuity to the whole f of M. It turns out that this operator hat F satisfies as its operator norm equals the Lipschitz norm of F, and that the following diagram is commutative. The commutativity of this diagram is nothing but a different way of writing this equality. Okay? But what matters here is that this hat mapping establishes an ontolinear isometry from Lip0 of Mx and the space of bounded operators from f of M to X. And so from certain point of view, our Lipschitz function, vector-valued Lipschitz function space can be seen as a space of operators. This will be relevant in the future. Okay? Let me finish this introduction to spaces of Lipschitz functions, recalling the well-known Max-Chain extension theorem, which says that essentially every Lipschitz function taking values in R can be extended in a non-preserving way. And more formally, if you have a Lipschitz function from a subspace of M to R, you can find an extension such that the Lipschitz function, the Lipschitz norm does not increase. As I say, this is probably one of the most important points to develop the theory of Lipschitz free spaces in real case, because when one replaces the scalar field R with C, what one obtains here is a multiplicative constant, the square root of 2. So you don't get an isometric version of Max-Chain extension theorem. And this is the reason why we are dealing with real Banach spaces in this talk. Okay. So once these spaces have been introduced, as I have heard several times in this Congress, it has been very popular since at least in the first edition of Weaver book, and a lot of properties of geometric and isomorphic nature have been analyzed in these spaces. We can say probably approximation property, the fact of being L1 and L infinity symmetrically, octaedrality, Daugavet, and so on. But these properties have not been analyzed in so deepness in the vector valued case. And one example where this happens is for the Daugavet property, which is the property I'm going to introduce right now. It was already introduced by Olaf, but I want to recall once again that given a Banach space X, it is equivalent, the fact that every rank 1 continuous operator from X to itself satisfies that the norm of T plus identity equals the 1 plus the norm of T. This is the original formulation that came from Ivor Daugavet paper of 63, where he proved that the basis of continuous function on 0, 1, every compact operator from CK into itself satisfies this Daugavet equation. But as a consequence of our work of Kades, Vitkoy, Sirotkin, and Dirk Werner for slices and later generalized by Roman Vitkoy, this is equivalent to the fact that given any point in the sphere, any epsilon, and every wake open set of the ball, you can always find somebody in W far away from X. So this property 2 means that whenever you take any X in the sphere and any wake open set, you can always find somebody here, which is 2 minus epsilon far away. So it is a property of the wake open set being extremely big in diameter. And this is in turn equivalent to a wake star version in the topological dual space. Okay, as I say, the paper of Kades, Vitkoy, Sirotkin, and Dirk Werner, they obtained the same result, but replacing wake open set with slices. Okay, so it seems that this property has not been analyzed in vector valued case, but yes in the real case. Why? Or how the proof works? How do we get a Lipschitz free space which is Daugavet in the real case? And let's see what happened later. Well, it turns out that the Daugavet property is very well described here in terms of a condition on the underlying metric space M. Given a metric space M, M is said to be length. If given any pair of points in M, you can always find a one Lipschitz mapping joining the points X and Y, defined from 0 to the distance Sy plus epsilon. This essentially means that whenever you have 2 points in your metric space, you can always find rectifiable curves joining them whose length is as close as you want to the distance from X and Y. This is equivalent formulation. When epsilon can be taken, we speak about geodesic metric spaces. And as you can imagine, easy and relevant examples of geodesic spaces are the Banach spaces, where the geodesics can be defined using metric segments, vector segments, I mean. Okay, and the play that length spaces play in this story is that as a consequence of a collaborative effort of in two papers, a paper by Kades, Wagner, and Dirk Werner, where some of results were proved and completed later by Garcia Lirola, Prohaska, and myself. As a consequence, it is proved that for a complete metric space, f of m has the Daugavet property if and only if m is length, that has this property that every pair of points can be approximated by the distance by length of curvature in them. Okay, and why this doesn't work for vector valued case? Okay, let's try to see how to prove the Daugavet property in the real case, and let's see where are the gaps. Okay, we will make use of this third condition. So we consider a Lipschitz function, an element in the dual of f of m, a positive epsilon, and a weak star open set, and we want to find somebody in W far away from F. Okay, we begin selecting somebody in W, and W satisfies that there are finitely many points and eta small enough with the property that whenever you take a Lipschitz function whose values at mi are near to that of H, then automatically G belongs to W2. So somehow the belonging to the weak star open set W does depend only on finitely many information of evaluation at M. Something that it is natural and follows since evaluation mappings form a dense expansion, linear expansion. Okay, once we have these points MIs, we can find a different point x0 with the property that given any r, you can find y in M, which is r close to x0, and so that the increasing quotient of f is big. X0 satisfies that when you take any ball centered at x0, then you can always find y where f has a big slope. And in a smaller, you can find another, and so on, and so on, and so on. So somehow, this Lipschitz function over length spaces, the Lipschitz constant can be approximated by arbitrarily close points, and even more localized. And indeed, they can be always found infinitely many points x0 satisfying that. This will be something relevant in the future. Okay, what next? Because we don't see still any problematic point. What do we do? Okay, if this works, where it doesn't matter how small the ball we take, we consider a small ball leaving the MIs out, and we want to construct a function which satisfies that at MI behaves like HI, and which is flat at some ball centered at x0. This is our function phi. And defined in this piece of M, this function is of norm nearly to 1 if the ball is of radius small enough. Extend by Max chain. Okay, what next? What we do next, we make here zoom, and we say, okay, here you can find points where f has big increasing quotient. So I will take somebody close to x0 where f has big increasing quotient, and I'm taking a function which is 0 out of this smaller ball, being 0 at the center, and touching here distance x0 and y. So we are finding another function which has big slope at a point near to x0, and extend by Mach chain. And what is the point then? We consider G as the sum of this phi and this psi. And the point is that if this the distance here is very big compared with this distance, the norm of this phi plus psi is very close to 1. What next? G at mi's behaves like phi because C is flat out of this ball, or in particular out of this ball. So the evaluation G of mi equals a phi of mi, or it is approximate. So somehow G will belong to W if we do well our work. And the increasing quotient of G at y and x0 is essentially the same to the increasing quotient of psi, because phi is flat here in this ball which contains that. And this makes that G and F behaves a pair where the slope is big and the norm of the sum is big. That's the idea, more or less. Okay, what happened in the vector valued case? Well, in the vector valued case, we have two problems. The first one is that here we are dealing with Weierstrass open set. So, okay, is Lipschitz a dual Banach space? Here, in our approach, was very important because Weierstrass topology was used because Weierstrass open sets were defined in terms of finitely many points on M. This should be false for Weik open sets. But there is another big point. Mach chain extension theorem is false for vector valued Lipschitz functions. This is a serious problem in order to construct this function and that one. So what we do? Well, try different techniques. Okay, concerning the fact that Lipschitz is a dual space, when the target is a dual space too, there is something we can do. Okay, we said that Lipschitz is, at the very end, a space of bounded operators. And it is well known, I don't know if it is well known, but it is known that this space of operators is a dual space where the target is. And in order to present a pre-dual, you have the projective tensor product, which is the completion of the algebraic tensor x, tensor y, under the norm exposed here. This is infimum of sum of norm of xi, norm of yi, where the infimum runs over all the possible ways of writing Z as a combination of basic tensors. It is known that the dual of this projective tensor product is isommetrically isomorphic to Lxy star, and the action in which a bounded operator acts on an elementary tensor is simply evaluating T of x. It is an element on y star, so it knows how to act on y. And extend by linearity and continuity, and it is isometry. And notice that by the very definition that this space is dense in the projective tensor product, sum of basic tensors is dense. Okay. We'll go back to try to see that f of m tensor x has the Daugavet property. Let's repeat the sketch before and let's see where are the gaps. As before, we take a norm1 function, an epsilon, a Weierstrass open set. Now we have Weierstrass topology to talk about. And as before, we look for somebody in W far away from F. As before, select any point. Still, that fact that Weierstrass open sets are defined in terms of finitely many information still holds. Now, there are finitely many points in M and finitely many vectors in X, with the property that if somebody is of norm less than 1, and the evaluation, vector evaluation at MIXI nears that of H, then G must belong to W. Okay, we save this point. What next? Next, we needed that all our Lipschitz function approximated Lipschitz norm at arbitrarily close point and localized somehow. But this is not a problem because in the vector valued setting, you get f of x minus f of y one minus epsilon. You can use an OR1 functional to compose here because of Banach theorem. And this is a real valued Lipschitz function where you can use the argument before. Okay, so somehow we can save it finding a suitable function that does exist, and you can find a different point x0 with that property. Here we have the first problem. We want to construct a function which is flat around x0 and acting as h at the mi points. We cannot do here because we don't have Mach chain extension theorem granted. So big problem here. And of course, we wanted to apply Mach chain extension theorem in that side, doing something similar, finding somebody and defining a function which is 0 out of a ball and touching the distance here. We cannot do it with Mach chain extension theorem. But okay, here it is not so relevant because we can use functionals of the form t multiplication by x star or t tensor x star. I wanted to avoid tensor, but okay. So somehow using multiplication functions by real value Lipschitz functions, you can use here a supported contain here Lipschitz function and multiply by x star, and okay, you can save this. Not that, but this. And the very last argument, it is just a matter of comparing distances in the metric space. It is not relevant, the vector valued case. So our big point here is how to construct Lipschitz functions which behaves like one fixed at finitely many points and doing it flat some other part of the metric space. This is our real problem. So what we need is, given any h, to find tilde h which behaves like h at mi's and being flat at some ball center at x0. Can we do it? Yeah, but not with Mach chain extension theorem. That is where we recalled a result of Philip Talinjowski, which appeared in his PhD thesis, which says the following. Given two positive numbers, you can construct a function which is 0 at the ball center 0 on radius r, which is the identity out of the ball of radius 0, center 0 on radius b. And if you define in the middle in such way, then the Lipschitz norm of f is smaller than b minus a. And in particular, up to working with translation, what you can prove is that you can find, given any point r and epsilon, you can find a small enough delta and a Lipschitz function from x into itself, which is the identity out of a ball center at x0 of your prescribed radius, which is flat at some smaller ball, and so that the norm is as close to 1 as you wish. What next? If we wanted to perturbate our function h, we can assume up to a perturbation argument that our h of x0 is different to h of mi. And then we can take r small enough in order to h of mi not belonging to h of ball center of h of x0 and radius r. Apply our function and find some ball around h of x0 where psi is flat and the identity out of a bigger one. Now compose h with psi. Clearly, it will coincide with h at the points mi. By construction, it will be flat at the pre-image of the ball around x0 by f, and the Lipschitz norm will be nearly 1. And putting everything in together, we were able to prove that if M is length indeed, the projective tensor product of f of m and x has a Daugavet property regardless x. And as I say, this solved a question of 2018 in the paper where we complete the characterization in the real case. Okay, I have to confess that when I told you the characterization of the Daugavet property, I told you half of the truth, which is the complete truth. The complete truth is that it is equivalent that f of m has a Daugavet property that m is length, and the fact that the dual has a Daugavet property. If you think in the very original operator definition of Daugavet property, it is clear that the Daugavet property passes from a Banach space into its predual. So somehow proving that Lipschitz has a Daugavet property is harder rather than the Daugavet property of f of m. That is why I started by there. Now, if our result were good enough, we should be able to prove that m length implies not only that f of m tensor x, but Lipschitz of mx has a Daugavet property regardless x. And the answer is yes. And I will tell you a sketch of a sketch, which means that I will be even more sloppy than previously, in order to tell you the ideas, but avoiding this kind of technical details, because they are quite more delicate. Okay, we begin with two Lipschitz functions and a positive epsilon. If you think in this geometric characterization, I would need to take a wake-open set in the space of Lipschitz function and find somebody inside. So I would need to deal with weak topology in Lipschitz. This is something crazy if you think that there are cases in which our Lipschitz is L infinity, capital or small L infinity, there are examples of both, make us think that we are not success in describing the weak topology of Lipschitz. In order to do that, we will try to do the following. Let's find a sequence Gn which is weakly convergent to G, so that all the terms are far away from F and that the Lipschitz function converges to 1. If I'm able to do this, once I fix a wake-open set containing G, for some large enough term, I can find a large term so that G over its norm will belong here. And if all the terms are far away from Gn, I will find somebody here. I will try to prove something stronger, but which in our purposes is easier in our context. Okay, what now? I'm going to find infinitely many points Xn where f has big localized increasing quotient. This is something possible by the length definition. That is that I can find infinitely many points with that property. And if I found infinitely many points, I'm going to separate them by pairwise disjoint functions. And now the idea is using Talinjowski theorem in order to construct Cn, a Lipschitz function which agrees with G out of the ball of center Xn and Rn, and Cn being flat at some smaller ball, and of norm converging to 1. And using this, I'm going to take Lipschitz functions which take a big slope, somebody very close from the center of these balls. And I'm going to take Lipschitz function which has somebody inside with big slope, sharing big slope with f, and so that Sn is 0 out of a smaller ball as we did there. Okay? This is the idea. And now, We take that Cn minus G and phi n are pairwise disjoint support function by construction, because the support of these functions belongs, all of them, to this ball of xn Rn, which are pairwise disjoint by construction. And a result of Cascales et al. Implies that these two sequences are weakly null because they are bounded. And now the point is that if the distance from xn to yn is very, very smaller than this Sn, and this Sn is quite smaller than our Rn, then a function, as in the real case, allows us to get Gn converges to G, because this Cn converges to G, and this is weakly null, and all of them far away because phi n and f shares points where they have both big slope. And this is essentially the idea. I didn't want to enter in deeper details, okay? But this is the main heart of the proof. And I'm essentially done. I want to finish my talk telling a story, because as I have said several times, I'm getting old, and one way of proving it is a finishing talk with stories. In September of 23, in the conference Easy to Define, Hard to Analyze, first conference on Lipschitz free spaces, I presented a talk based on a previous version of this work with Ruben Medina, and I presented the following as a sufficient condition for the Daugavet property in the tensor. This property essentially demands that you can find functions from M to M of norm nearly 1 acting as the identity at finitely many points and being flat inserting ball. And with this idea, we were able to prove the Daugavet property for f of m length and a Banach lattice X. And Richard Smith kindly let us know the result by Talinjowski. And with that, we were able to remove any condition on X, and also we were able to strengthen our theorem to get not only the Daugavet property in f of m X, but also on the space of Lipschitz function. I like to tell this story in order to make publicly my acknowledgement to Richard Smith, and also because I think this is a very nice story which shows that the real progress of science is based on cooperation and not on competition. I finish with the list of references I have based on. This is the paper with Ruben Medina where every of these appears. This is Talinjowski thesis where the result appears, as I know, first time. And I thank you, George, again for your patience.